Hey AP Stats, it's Mr. Luneski here to teach you about Chapter 20, which is about the introduction to hypothesis testing. Throughout the rest of the year, chapters 20 up to 27, this is basically what we're going to be doing. So we're going to kind of slowly introduce you to a different test each chapter. So chapter 20 is going to be on a 1 proportion z-test. This is what we have been using quite a bit with our confidence intervals, so some of this should seem a bit familiar to you. So this is kind of what the whole year has been sort of accumulating to, is this idea of testing a hypothesis that, if you go out into the world to kind of actually do your experiment, collect your data, draw a conclusion. We're trying to gear up towards the cause and effect relationship, so to speak. When you're testing any hypothesis test that we do in class, we're going to be using the normal model, and then we're going to be testing the hypothesis, and that's going to be using a 4-step procedure. So this process stays the same from chapter 20 to 27. So these 4 steps are never going to change. It's going to be the same 4 steps the whole time. So the 4 steps, step 1 is to state the hypothesis. Step 2 is to state your conditions and your procedures. Step 3 is to show your work, your mechanics, and your model. And then step 4 is to draw your conclusion. You're going to hear me refer to this as the box method. So typically on a problem, you're going to just draw a little cross here, and then in this box you would do the hypothesis. This box here you would do your conditions. Over here you'd do the mechanics, and here you'd write your conclusion. That's sort of a method that they allow on the AP test, but it's also fine if you write this in paragraph form. So to start off, use the 4-box method, but you might find yourself getting comfortable writing it as a paragraph as we move on in the rest of the chapters. So as I mentioned, today the focus is going to be on a 1 proportion z-test, and so we abbreviate it as a 1 prop z-test. So that just means we're working with categorical data. There's 1 variable. There's no comparison of groups. It's just 1 proportion. So what I'm going to do is kind of walk you through each individual step to kind of just help you out a little bit. Nope, too much. To just kind of help you out a little bit to understand what needs to go in each box, and then we'll look at an example together. So step 1 is the hypotheses. So there's going to be 2 parts that you have to state. One is called the null hypothesis. The other is called the alternative, or sometimes it's referred to as the alternate hypothesis. So let's talk a little bit about the null. The null is basically a claim about an unknown population. We would denote that as H sub O. You will hear me referring to it as the hoe. We call it a null because it's skeptical of the world. So generally in your null hypothesis, you're basically saying nothing has changed, everything's sort of staying what we think it is. And basically what we're doing is, if you remember from chapter 18 and 19, we have these sampling distributions, and we're basically saying, yeah, this sampling distribution's fine. The purpose of the experiment and the actual hypothesis testing is to try to prove that that model is bad, and we're trying to see, do we have enough evidence to reject the null? So in other words, we're asking, is it wrong enough to reject this null? Because ideally that's what we want. We want to try to prove something's wrong. The alternative, or the alternate hypothesis, is denoted as H sub A, essentially hypothesis A. We call it the ha. So you'll often hear me say the ho-ha. Ho-ha is referring to the null and the alternate. And so basically with the alternate hypothesis, that's kind of what you're trying to prove. So there's essentially 3 types of tests that you can do for your alternate. A two-tailed test is basically if you're just looking for a general change, you're saying it's different from what you're claiming. A one-tailed test means that something could either be increasing or something could be decreasing. Typically we do one-tailed tests, but occasionally the two-tailed test is acceptable as well. One-tailed tests are typically more interesting because you're actually showing an increase or you're showing a decrease. So that's actually going to be decided in the first step in your process. So I wanted to show you an example of what some of this would look like. If I were doing a two-tailed test, and let's just say we were talking about the proportion of students who love pizza is 20%. A two-tailed test, the null would be, yeah, p is equal to 0.2%. Nothing has changed. Oh, I'm claiming it's 20%. Cool, it stays 20%. Whereas the alternate, if I'm just trying to disprove, oh, it's not 20%, but I'm not being specific, is it higher or lower, I would just say p does not equal 0.2. Notice here I'm using p, not p hat. The idea of the hypothesis test is that we're making a generalization about the whole population, so we're going to use p for our hypotheses. If I was trying to do a one-tailed test showing something was increasing, my null would still be p equals 20%. If I was trying to prove that more students liked pizza than 20%, I could say p is greater than 20%. And then a one-tailed decrease test basically would just say p is less than 20%. So the one thing I want to point out to you is that the null here, if you notice, the null is always equal to, and that will always be true. Notice I'm not saying, oh, it's less than or equal to, or it's greater than or equal to. I'm just saying it's equal to. And that will always be true for the null. So always think your null hypothesis will be equal. Okay, so here's just an example problem of practicing sort of writing the ho-ha. So it says a governor is concerned about his negatives. The negatives refer to the percent of state representatives who express disapproval of his job performance. His political committee pays for a series of TV ads in hoping that they can keep his negatives below 30%. Then they use a follow-up polling to assess the effectiveness. So if I were to write a hypothesis test to see are these ads effective, what would that look like? Well, the null, again, would be that it's staying 30%. So notice we're not really investigating are the ads not working and maybe it increased. We're just saying it stays the same. You're claiming 30, let's say 30. The purpose of the ads is to keep the negatives below 30%. So we're then going to investigate is p less than 30%. When you write your hypothesis, it's not enough to just say this stuff, because again, most people might not understand this notation, so the idea is you then have to translate that a little bit into words. So saying what exactly is your null, what is your alternative saying? So null is claiming the governor's negatives stay at 30%, the alternative tells us his negatives will be below 30%. So that's an example of our hypotheses. Step 2 in our 4-step process are your conditions and procedures. This really shouldn't seem anything new. Basically, you're just listing the conditions. So for a one-prop z-test, it's the 4 conditions that we're used to. As we progress through the rest of these chapters, you are going to notice that some of the conditions change for different tests. But for now, we still have independent, random, less than 10%, and then NP and Q have to be greater than or equal to 10. As a reminder, this is not an optional thing. You have to use full, complete sentences, using vocab, using context. It's not enough to just put check marks. Don't just say NP, NQ greater than or equal to 10. You should show the numbers of expected failures and expected successes. And then you should always follow up once the conditions are met to say something along the lines of, since the conditions are met, we will use a normal model. And then something else that we have to add to this is say what test you will use. So for right now, the only test that we have is a one-prop z-test or a one-proportion z-test. So you might be thinking to yourself, what happens if these conditions are not met? Because this does happen in the real world. Well, if this happens, if we get to a problem and you feel like, wait, this condition is not met, typically that doesn't mean you just stop doing the problem. A phrase that is often used is proceed with caution. This is basically just saying that once you state a conclusion, that you're not claiming it as this is 100% accurate. There may have been something, some foul play, that maybe the sample wasn't random, there was a bit of bias involved. So anytime you get to a problem and you feel iffy on the conditions, you can kind of say proceed with cautions, but you should state what your concerns were. So don't just get to a problem and be like, proceed with caution. So tell me why you're proceeding with caution. For the most part, though, in this class, conditions are typically always met. Okay, so step 3 are the mechanics. For the mechanics, basically, you are just showing your work. This is kind of your workspace to say, here's, my x value, so sample size. You have your x value, your n value, the observed number of successes, sample proportion, your p-hat, whatever type of test you're doing, you're kind of showing what those numbers are. You should draw a curve depicting what the sample model looks like. So I want to remind you that the sampling model here is always based off of the null hypothesis, because the idea is we're trying to prove that that model is wrong. And so it says locate the p-value and shade the curve correctly. And so to find a p-value is kind of something new here. P-value, when we find that, typically we're either going to use the calculator or we're going to use something that you've seen before, the normal CDF. So if you're doing a left-tailed test, and forgive my drawing, I don't have a pen with me. If we're doing a left-tailed test, you basically are doing, you're basically doing a normal CDF where this is your upper bound. And basically the p-value tells you what percent your sample, the likelihood of your sample occurring is. For a right-tailed test, that just means that it's a greater than problem, so you would be increasing. So this would be your lower bound, your upper bound would be positive infinity. And then for the two-tailed test, you only have to do a normal CDF for one of the bounds. So it really doesn't matter which one you pick. You can pick the left bound or the right bound. Find that probability using normal CDF and then multiply by 2 because it's symmetric. So two-tailed means you're technically checking both of these. So you can either take the time to do the normal CDF for both tails and then add them together, or just find one and multiply by 2. So again, that probability, that once you find that is called a p-value. So what exactly is the p-value? The p-value is the likelihood of getting your sample, p-hat, from a pile of p-hats. So if you remember in those activities where we all put little stickers up on the board, we were all making these little p-hats. And basically when I find a p-value, that's saying what's the probability of me reaching into that pile of p-hats and picking out your particular sample to get your sticker. So basically this is the probability of your sample's results occurring naturally or by random. If you get a p-value that is almost 0, that basically is saying there's almost no chance of us getting that particular p-hat, of getting that sample through natural variability. So therefore, your null hypothesis most likely isn't true. Because remember, the null hypothesis is basically claiming here's this model and it is accurate. And so we do something called rejecting the null hypothesis. Okay, so the last step, step 4, the big one, is state your conclusion. Basically, stating your conclusion is when you link the p-value to the decision in context, and then you state your decision about the null hypothesis. So your conclusion should always, 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 always be about the null. So you have two types of conclusions that you can make. You can either reject the null, and when you reject the null, what you're saying is that there is statistically significant evidence. Or you can do something that's called failing to reject the null. That's basically saying there's not enough evidence. You will enter every single question under the assumption that the null is true. Because basically if you go into the problem thinking that you're right, you're kind of not really working with the null. You're kind of creating a bias towards your response. So this says that your calculations give you a number to help you decide if it's likely that the results are random. Again, that is called the p-value. A p-value that's very low tells you that you should reject the null. And my buddy Snoop Dogg has a little saying that if the p-value is low, then the hoe must go. In other words, reject the hoe. P is low, reject the hoe. So that's a little saying we'll have in stats. Sounds a little weird. All right, so a couple little things to tie all this up, and then we'll look at an example problem. Is that there is no magical p-value. So I've been talking about like, oh, if the p-value is low. Well, what exactly does that mean? What's considered a low number? It really is a matter of opinion. A p-value of 0.08 as a change in teen smoking can be considered very low. But a p-value of 0.08, and if you're talking about the strength of a rivet in holding a plane's wing together, that could be a really big difference. So typically, the p-value that we use is 5%. So any p-value that's less than 5%, we typically will reject the null. Problems sometimes will state what p-value to use. If a problem doesn't state what p-value to use, just assume that it's 5%. You will never, ever, ever, in your conclusion, say accept the null. So what you need to think about is in a jury delivering its verdict. Whenever someone goes to court, they are found guilty or not guilty. They never say guilty or innocent. It's just saying we didn't have enough evidence to prove that you are guilty. And so when I go here and I say, reject the null or fail to reject the null, all I'm saying here is that I didn't get enough evidence to say that this is wrong. So never, ever, ever say accept. Okay, so what exactly am I looking for in this type of problem? You're basically asking yourself, are you surprised with the result? Should you reject the null? How surprised are you? What is the p-value? And then what would not surprise me? So we can use confidence intervals still to figure out what values would not surprise me. Any value that falls inside a confidence interval of 95% roughly, that shouldn't surprise you. So what we're going to do now, we're going to take a look at an example problem. So this is actually what the whole thing looks like. I'm going to zoom in on each box individually here, but I just want to read the problem first so you get an idea of kind of what we're testing here. So this might work, it might not work. Okay, let me hide all this junk. Probably can't read all this actually, now that I'm looking at my bounds here. I'll just read the problem. You can read along with me. So it says a 2007 report from the U.S. Consumer Product Safety Commission claimed that at least 90% of all American homes have at least one smoke detector. A city's fire department has been running a public safety campaign about smoke detectors consisting of posters, billboards, and ads on the radio and TV and in newspapers. The city wonders if its efforts has raised the local level above the 90% national rate. Building inspectors visit 400 randomly selected homes and find that 376 have smoke detectors. Is this strong evidence that the local rate is higher than the national average? So, box 1 is the hypothesis. So what the problem was initially asking us, let me go back out here. So in our little 4-box method, when we make our little cross here, box 1 is going to be the hypothesis. So what was the problem asking? The problem was asking, were these ads effective in getting our one city's smoke detector rate above the national average of 90%. So remember, the ho-ha, the null basically claims that no, it hasn't made it bigger, so we just assume it stayed at 90. We assume everything's normal, nothing's changed, it's 90. The alternative, though, is stating, yeah, the p-value is going to be above 90%. And so remember, you have to write the ho-ha and you have to write a little sentence sort of explaining what the ho-ha is talking about. So null is saying the city's smoke detector rate is 90%. The alternative states that the city's rate is above 90%. So that's all box 1 is. Box 2 is to check your conditions. Your conditions and procedures are always based off of the population, not the sample. So you do not bring p-hat into the picture until box number 3. So we should not be mentioning the sample of 376 out of 400 smoke detectors anywhere in here. So We have 400 randomly selected homes that we assume are independent of each other and less than 10% of all homes in the city. Notice what I covered. Random, independent, less than 10%. I covered that all in one sentence. And so, what do we expect? NP/NQ. So our sample size is 400. The p-value is that 90%. So remember, the model is claiming, oh, it's 90%. So if we assume that the p-value actually is 90%, or the population parameter is 90%, 400 times 90% gives me 360. NQ would then be 40. So both of those are greater than or equal to 10. So all of the conditions are met. Therefore, we can use a normal model, and we will conduct an upper tail 1 proportion z-test. So notice I specified which type of tail test I was doing as well. You should also kind of specify that. So that's box 2. What does box 3 look like? Box 3 was our work, our mechanics. So now here's where we introduce p-hat. So what was our x value? How many successes did we have? We had 376 successes out of 400. Our p-hat, whoops, I forgot to actually write that down. This comes out to be 94%. So if I do 376 out of 400, that's 94%. And then we need to find standard error. So remember, standard error is square root of p-hat times q-hat divided by n. So we get a standard error of 0.015. We should draw our model. So our model looks something like this with 90% in the middle. So this is what the null model looks like. This is what the null is claiming as fact. And what we are trying to do is prove that we're not doing that, that it's wrong. And so our p-hat value falls over here at 94%. So the cool thing about standard error and the normal distribution is if we go 2 standard deviations out, we can see right here, hey, we're beyond 2 standard deviations, so we should know that this is unusual, that this is an outlier. And so we can kind of use that to our benefit. So I know a lot of you like to just ditch the model and not use it. I think it comes in handy. Now, unfortunately, you can't just draw the model and call it a day. You actually have to calculate a p-value now, and we're going to talk about that as we move on through the unit. So, how can we calculate the p-value? We can calculate that using our normal CDF. So our normal CDF, we're saying 94% or above, kind of up here. So 94% is our lower bound, upper bound, 999. Our mean is 90%, and then our standard error comes right here. So you should get a p-value then of 0.003. So what does that mean? That means the probability of me sampling 400 households and getting 376 households to have smoke detectors in them, the probability of that sample happening is 0.3% under the assumption that the null is true. So because that value is super, super small, what do? Box 4, our conclusion. So the way that we write a conclusion typically goes along the lines of this. We say the p-value is low or the p-value is high, depending on the problem. So if the p-value is low, the hoe must go. So p-value is low, therefore we reject the null hypothesis. There is statistical evidence that the city has a higher rate of smoke detectors than the national rate of 90%. And so that last little bit there is just linking it all together via context. And that's basically it. It seems like a long process, I know, but once you get used to it, it actually isn't that terrible. Kind of just becomes very repetitive. All right. Thank you for watching. Appreciate the time. I know it, and now you know it.